Hello everyone, this is Steven Chimelis, and today I'm going to talk about the role of power electronics in the evolution of photovoltaic resource integration. So let's begin. So the world's increasing demand for energy for domestic and industrial uses has fueled the need to push for alternative energy production methods and ways of integration. Among these alternatives is the introduction of solar energy into the national electricity grids, and the injection of solar energy into the electricity grids decreases the rate of consumption of non-renewable energy resources. And it also enhances sustainability and environmental conservation by reducing over-reliance on fossil fuels, which causes significant environmental pollution. The introduction of photovoltaic systems has engineered the green energy revolution using the sun's ever-available power and converting it into DC or AC power. And power electronics has played a very significant role in the evolution of photovoltaic resource integration. So in this presentation, we will take a look at the role of it. So power converters are essential in controlling the flow of power between two power systems by changing electrical energy's character from direct current to alternative current, or from one voltage level to another. So the classification of converters can be best made according to their input and output signals waveform, or whether they are alternating or direct currents. In this regard, these are four types of converters that we're going to talk about today. DC and DC power converters are electronic circuits that change DC operating currents or voltages. They are specially designed to transfer power between the inputs and outputs of the system in one direction. So these have a special application in low power circuits like cell phones and personal computers. So for DC-AC converters, commonly known as inverters, are fit with topologies that can enable them to obtain a given power amplitude and frequency of AC voltage without applying the normally intermediate direct current stage. The type of converter works like a power electronic oscillator, which is a circuit that produces repetitive signals like sine wave output signals. AC-DC converters, however, are involved in the system's rectification process. Hence, they are also known as rectifiers. Apart from supplying power, they are also used in detecting radio signals. And the rectification process can be a full wave or half wave. Half wave rectifications allow only one of the input waveforms supplied to achieve the desired outcome. On the other hand, full wave rectifications allow the entire input waveform to convert to attain the desired output signals. AC converters convert AC input signals to AC output signals using an arbitrary amplitude. And during the transformation, the AC-AC converters can change the frequency depending on the complexity of the converters used. And the type of circuits employed determines the efficiency of these systems. However, high power reliability and density can be achieved with a one-stage conversion. Due to the introduction of other interfaces, there are issues and challenges related to photovoltaic resources grid integration. The issues can be categorized into technical, metering and rates, contractual, certification, and warranty at research and development challenges. Technical challenges in photovoltaic systems arise due to safety, islanding, identification and traceability, measurement and reporting, codes and standards, and power quality. Most utility interconnected PV systems have very high DC voltages before being converted to standard AC currents. Such voltages have a high potential for fire hazards, posing a safety risk to the engineers. Proper wiring needs to be done to ensure that any DC power-related hazards are significantly minimized. Islanding is among the most common safety problems for photovoltaic systems. It can occur when a portion of the system comprises both generation source and loads are fully secluded from the system but remain energized. Contractual challenges include fees, liability insurance requirements, and related charges. Liability insurance is essential in protecting the workers and utilities in case of accidents attributed by the PV system's operations. Solar PV systems are mostly affected by the abnormal ability of solar irradiances, which might interfere with the constant voltage output supply. To overcome this problem, the PV power electronics applies various DC-DC converter designs, and power production. Several DC-DC converter designs are currently in use in the regulation of input voltage, and they can be classified into oscillated and non-oscillated DC-DC converter designs. When developing the oscillated DC-DC converter designs, an electrical barrier is formed using higher frequency transformers, which are placed between the built transformer's input and outputs. The essence of this modification is to offer protection to sensitive loads. And on the other hand, non-insulated DC-DC converter designs are simple and are characterized by the absence of the electrical barrier. So this omission makes them less costly and as well gives them simple designs. The increase in efficiency, lowering of operational costs, and pollution reduction are the biggest benefits of PV systems and have led to a wide range of their application. First, PV resources can be used in utility interacting applications where the AC power converted from DC can be used to power households and can also be sold to the main grid. Second, PV resources can be applied in supplying energy and voltage to standalone systems. Standalone systems make direct use of the generated AC power and do not rely on grid or utility connections. And batteries and conventional generators are normally used as backup systems, especially at night or in poor sunlight. Thank you all for your time, and I hope that you enjoyed this presentation and learned the importance of power electronics and PV systems. Take care and be safe.